function, Ms. Stewart, and we've been working with implicit functions quite a bit. Notice I have the x's and y's kind of all jumbled up. That's what makes it implicit as opposed to explicit. And you kind of know how to take the derivative of this already. Well, Ms. Stewart, you certainly know how to take the derivative.
Well, thank you, Mr. Haas.
But we've been really thinking about derivatives as slopes, as change in y over change in x. So in other words, everything, like when we took the derivative of an x term, we had dx dx. When we took the derivative of a y term, we had dy dx. Again, another y term, it would be whatever it is, dy dx. But let's say we were taking the derivative of a function which was not changing in the way that we've been thinking of it. In other words, it's not really just slope. It's not everybody changing over the x-axis. Let's say everything was changing with respect to some other variable, like perhaps time. What do you think? Am I blowing your mind?
I'm liking this.
All right.
This
So
is
what
great.
would that look like? So it's really it's implicit differentiation, which you already know how to do. I'll take the derivative of this first guy. So of course that would just be 6x. I could write, if this were regular implicit differentiation, remember I could write dx dx. But again, in this special function, I'm going to pretend that everything is changing with respect to time. So I'm going to write dx dt. dt standing for time. Difference in x values over difference in time. How about this next guy? Ooh, that's a product rule. You already know how to do this. Derivative of the first guy is just 2, but I have them take the derivative of x, dx dt, times the second guy, plus the first guy, times the derivative of y, dy dt. So every variable is changing here with respect to this third variable, time. And finally, I'm up to this last guy, and that would be 15y squared. Again, I'm taking the derivative of a variable, so I'm going to stick on a dy dt. Now this is some kooky function, and I'm not even going to solve it for any of the variables, but this again is how you would take the derivative if every variable was changing with respect to time.
So that dx dt really is the rate, right? At which x is changing as time changes.
That's exactly what it is.
And
it's how fast x is changing over time, how fast x is changing over time, but y is also changing over time. Every time I take the derivative of a y term, oop, did I mess something up here?
No, that's right. You did the product
okay.
right.
I was looking at the wrong term. I think I'm all set. Yep.
You are. So those are all rates still.
They
so
are all
derivatives
rates.
are rates, but they're not slopes as we've been thinking
well,
of
but
them.
you know, slope is really a rate of change,
Yeah.
and I think we've been using those terms interchangeably.
That is
So
really
slope or a rate of
cool,
change.
Mr. Haas.
So this is what it would look like if you were taking the derivative with respect to time.
Love it.
Time